Dear students, today we can revise the topic heat transfer. The transfer of heat energy from one body to another, from one place to another. It may happen through three important processes: conduction, convection, and radiation. You must know what is the basic difference between the conduction, convection, and radiation. In conduction, it is happening without the actual movement of the particles in the medium, and is happened only for solids. But for convection, it is happened due to the actual movement of the particles, and is for fluids, for gases and liquids. But radiation, the material medium, is not necessary and is said to be the quickest mode of heat transfer from one body to another with a separation. At first, we can go through the thermal conduction principle, the law of conduction. Under steady state, and keep in mind the steady state means at that condition, if we just take different cross sections with a separation, the change in temperature with the separation is a constant. At that condition, the rate of flow of heat through a cross section A, length L in time T, when its ends are at temperatures T1 and T2, we can say the rate of flow dq by dt is proportional to the area of cross section and to the temperature gradient, and that proportionality constant, that is called the coefficient of thermal conductivity. And keep in mind, it depends purely on the material, not on the dimensions. Here the negative sign implies, and if you just look the location of the point from the hot end, that location increases, we can say the temperature decreases. So this law is very important. The rate of flow of heat energy dq by dt equal to minus Ka into dt by dx. While solving the problematic situations, you must compare that conduction process with the electricity. And there we can say the flow of charges I is nothing but equal to the potential by distance. Similarly, here you can compare, in place of current here, the rate of flow of energy, and in place of potential here the term the change in temperature. Then there is a concept, the thermal resistance, the resistance offered by a material to the flow of heat energy, and that is in mathematically we can write as the thermal resistance is equal to L by Ka. Keep in mind here the length L, K, the coefficient of thermal conductivity, and the area of cross section. Look, the two problematic situations. We have to find the equivalent conductivity for heat flow when the slabs are in series and then in parallel. In series in the sense, keep in mind, at any cross section we can say the heat flow is a constant. So for the two different layers, we can say dq by dt for one should equal to 2. And hence, like in electricity, we have to add the individual resistances. So Rs is equal to Rn plus R2. And hence we can say for effective material, L by Ka equal to L1 by K1A1 plus L2 by K2A2. If we just take the condition as L1 equal to L2 and A1 equal to A2, we can replace the two material with a single one having the thermal conductivity equal to 2 K1 K2 by K1 plus K2. But in parallel, that rate of flow is divided. The heat energy flow is divided among them. So the total one we can write like that. So if we put the value in place of resistance, in place of rate of flow, we can write as 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So we get the equation K1A1 plus K2A2 by K1 plus K2. So if A1 equal to A2, and we can say that is equal to K1 plus K2 by 2. So these are the very important two concepts while dealing the thermal resistance. And another very important concept in relation to the conduction, the growth of ice on lakes, especially in colder regions. The time taken by the ice to grow from a thickness x1 to x2 is T equal to half rho L by Kt into x2 square minus x1 square. And keep in mind, here rho the density of the ice, the thermal conductivity of the ice as K, and the surrounding temperature as minus 2 degrees Celsius. And we can move with some problematic situations at first. The coefficient of thermal conductivity of copper is 9 times that of steel. In the composite cylindrical bars shown in the figure, what will be the temperature at the junction of copper and steel? As I look the figure, we can simply use the temperature gradient concept for this much layer should equal to this much layer. Then we can arrive with a very good equation to find that junction temperature theta is equal to K1 theta 1 L2 plus K2 theta 2 L1 by K1 L2 plus K2 L1. And is given the thermal conductivity of the copper is 9 times that of the steel. So you can put the values and you get the answer as 75 degrees Celsius. We can quote the choice as 1. And here, the next question, a good question. 3 rods of the same dimensions have thermal conductivities 3K, 2K and K. They are arranged as shown in below. What will be the temperature T of the junction? Look the figure. See, and there we can say, like the current I is equal to I1 plus I2, we can quote here the heat flow, the total value equal to H1 plus H2. Then it becomes so simple as a K A into the temperature gradient. So we can write the substitutions. So you get the answer. A simple concept. The rate of flow is the sum of the two. Look at another good question. Ice starts freezing in a lake with water at 0 degrees Celsius when the atmospheric temperature is minus 10 degrees Celsius. If the time taken for 1 centimeter of ice to be formed is 12 minutes, the time taken for the thickness of the ice to change from 1 centimeter to 2 centimeter will be. We know the concept here. The time taken by the ice to grow from a thickness 0 to x is nothing but half rho L by Kt into x square. So between, if we just take the time interval from 0 to 1, from 1 to 2, from 2 to 3, so we can just take delta T1 is to delta T2 is to delta T3 is equal to 1 square minus 0 square is to 2 square minus 1 square is to 3 square minus 2 square. So 1 is to 3 is to 5. So according to our question, delta T1 is given as a 12 minute. So what is delta T? So it should be 3 times. So equal to 24. 3 into 12, it must be greater than 24. That means it must be 36. It must be greater than 24. So it's equal to 36 minutes. So the answer becomes 4 as the choice. We can move to the next good concept, a simple concept, convection. The thermal energy is transferred from one point to another by the actual movement of the heated material particles from a place of higher temperature to another place of lower temperature. And keep in mind, it has happened in the normal cases of liquids and gases. There are two important types of convection processes: forced convection and natural convection. Keep in mind, if the heated fluid is forced to move by a blower, fan or pump, the process is called forced convection. Our blood circulation, we can say, is the forced convection as one of the very good example. The natural convection, because of the density difference, takes heat from bottom to the top, while forced convection in any direction. But keep in mind, the natural convection can't take place in a gravity-free region. So the gravity is the main thing for a natural convection. The radiation. The process of heat transmission in the form of electromagnetic waves is called radiation. What do you mean by black body? A body which absorbs completely all the radiations falling on it. In the normal cases, the lamp black is 96% black. The platinum black is 98% black. And we can say the furthest black body is the nearest approach. Look, a sphere with a small opening and inside with a projection, and is coated with a lamp and a platinum black, and is nearest approach to a perfect black body. Then we have to move it to some of the basic terms in relation with the radiation. The first one, the absorptance or absorptive power. It is the ratio of the amount of thermal radiations absorbed by a body in a given time to the total amount of thermal radiations incident on it. So absorbed by incident. So that is called the absorptance. But emissive power means E of a body at a particular temperature is the total amount of thermal energy emitted per unit time, per unit area of the body for all possible wavelength. So you must know the difference between E and A. And another concept, the emissivity, entirely different concept. It is a ratio of the total emissive power of a body to the total emissive power of a perfectly black body. We must know, in the examination point of view, the coming two laws are very, very important. The first one, it proves a good absorber is a good emitter, especially in the case of a black body. The ratio of the emissive power to absorptive power is the same for all surfaces at the same temperature. And is equal to the emissive power of a perfectly black body. So we can say for different cases as E1 by A1 equal to E2 by A2 equal to, but it should be equal to capital E for a perfectly black body. For a perfectly black body, you know, the A value should become 1. This next one, the Stefan's law. The energy emitted by a black body per unit surface area per unit time is directly proportional to the fourth power of its absolute temperature. Then we can avoid the proportionality by multiplying with a constant that is called Stefan's constant and take the value as 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. A very, very important law. But if the given body is not a perfect black body, then you have to multiply with the emissivity factor. Look, the very important two concept, the cooling by radiation. A body at a temperature T is in a surrounding temperature T0. The rate of cooling, the change in temperature with the time is equal to epsilon A sigma by mc into t raised to 4 minus t0 raised to 4. Look the graph. So after some time, the temperature is equivalent to the surrounding temperature. The very, very important concept is the Newton's law of cooling. The rate of cooling of a body is directly proportional to the temperature difference between the body and the surrounding temperature. But keep in mind, the surrounding temperature difference is small. So we can say as minus dt by dt proportional to t minus t0, where that constant is that value. While solving the problematic situations, you must know this concept. If a body cools from T1 to T2 degrees Celsius in a time T with the surrounding temperature T0, then we can say T1 minus T2 by T equal to K into T1 plus T2 by 2 minus T0. If equal masses of two liquids having same surface area and cool from same temperature T1 to T2 with the same temperature of surrounding T0 in the interval T1 and T2, we can say as C1 by C2 equal to T1 by T2. So in the Newton's laws of cooling, that is applicable only when the difference in temperature is so small. See, the very important next concept, the Wien's displacement law. The wavelength corresponding to the maximum emission radiation decreases with the increasing temperature. That means the lambda m is proportional to 1 by t. So lambda m into t is a constant. That is called the Wien's constant. That value is 2.89 into 10 raised to minus 3 meter Kelvin. The solar constant. The solar radiant energy received per unit area, per unit time by a black surface held at right angles to the sun's rays and placed at the mean distance of Earth is called solar constant. That value is 1340 watt per meter square. We can go with some problematic situation. A good NEET question. An object kept in a large room having air temperature of 25 degrees Celsius takes 12 minutes to cool from 80 degrees Celsius to 70 degrees Celsius. The time taken to cool for the same object from 70 degrees Celsius to 60 degrees Celsius would be nearly. So you can use the simple concept there, and there we know as a dt by t equal to a constant into t minus t0. So we can take dt as a t1 minus t2 by t equal to k into T1 plus T2 by 2, the average value temperature minus T0. At first we can put the values and you get the value, the constant K. Then we can apply for the second case. So you get the answer. So that relation is more important. And we can move to the next question. See, the power radiated by a black body is P, and it radiates maximum energy at wavelength lambda 0. If the temperature of the black body is now changed so that it radiates maximum energy at the wavelength 3 by 4 lambda 0, the power radiated by become NP, the value of N is. So we can relate the first one, the Wien's displacement law. So lambda proportional to 1 by t. So for the two cases T1 by T2 equal to lambda 2 by lambda 1. But keep in mind that wavelength should be maximum. So it is given as a lambda 2 as a 3 by 4 lambda 0. So we get the value T1 by T2 equal to 3 by 4. But we know the power that is proportional to fourth power of its temperature. So P1 by P2 equal to T1 by T2 the whole raised to 4. So 3 by 4 raised to 4. But it is given that P2 is n times of the initial. So by substituting you get the value 256 by 81. A good aspect. The two circular disc A and B with equal radii are blackened. They are heated to the same temperature and are cooled under identical conditions. which inference you draw from their cooling curves. So we have to relate with the specific heats, and already you know the rate of cooling is proportional to 1 by C. So the rate of cooling varies inversely as the specific heat. So we can certainly say from this one, if that tan theta, the slope is great, means the specific heat is small. So we can say the specific heat of A is less. So, and keep in mind, it's a part of a very important chapter, the heat and thermodynamics. So keep in mind, you can wait minimum 3 to 4 questions from this chapter, heat and thermodynamics, for the NEET exam, and maybe more than 5 questions for KEAM entrance examination. So you must do maximum problems, then you can get maximum rank in the coming entrance exams. God bless you. Take care.